This is Chapter 1 of the OCR Further Mathematics Pure Core Student Book 1. We're looking at linear algebra, precisely. We're looking at matrices. When you finish listening to me talking about what you need for your course, it's really worth looking at the series made by Grant Sanderson, you'll find as 3 Blue 1 Brown on YouTube, and his course The Essence of Linear Algebra. The first 3 or 4 videos there really give you a feel for the where linear algebra comes from and why it works in the way it does. Anyway, what's a matrix? Well, it's a relatively simple idea. It's just an array of numbers, a rectangular array of numbers. Each number, as you see, called an element. So those are some examples of matrices. And we give each matrix a name with usually a capital letter, and it's got dimensions, which is the number of rows by the number of columns. And if we look at that first square matrix there, we've got 2 rows and 2 columns. In the second matrix, we've got 2 rows again, but this time 3 columns, and so on. So it's defined in terms of rows and columns. We've got 2 by 2, 2 by 3, as I've said. The third one it's got 3 rows and 2 columns, 3 rows and 3 columns, 2 rows and 1 column, and 1 row and 3 columns. So it's quite important to get that the right way around. It's going to be a little bit useful later. Same number of rows and columns as in the 2 by 2 and the 3 by 3, or a 4 by 4 is called a square matrix for fairly obvious reasons. If you've got 1 row or 1 column, they're called vectors, and we'll deal with those in another place. So the first thing you have to do with matrices, which is essential and necessary, is transposition. Simple idea, you just swap rows and columns. So there you go. The first row has got -135, so that becomes our first column, -135. Our second row, 2 -96 becomes our second column. Okay. Now we could have a matrix which is just 1 square by 1 square, and that's just a number, isn't it? And we call it a scalar. Okay, and they, as I said, capital letters. Scalar multiplication is trivially easy. Each element in a matrix gets multiplied by the scalar. So for instance, if we have this matrix A here, doesn't matter about the shape, and we try to do 3 times A, we multiply all the elements by 3. That's all there is to it. Now we can kind of go backwards and divide by a common factor. So the matrix I've got on the left, 15, 25, 75, and so on, is the same as 5 times the matrix 3, 5, 15, etc., etc. Now addition and subtraction is pretty straightforward, as long as you've got what we call conformable matrices, and in this case what we mean is conformable matrices are ones which are identical in dimensions. So we can add a 2 by 2 to a 2 by 2, or a 2 by 2 to a 2 by 3, and it's exactly as you'd expect. We just add the corresponding elements, and that's it. Nothing clever about that. Doesn't matter about the size of the matrix, as long as they're the same principle holds, and there we go. Now, matrix multiplication is much more difficult. It's something you've got to practice quite a lot to really get the hang of. You've got to be quite patient with this. If you watch Sanderson's videos, he does explain why we do this together, and it's to do with this idea of transformations, which matrices are very important for. So you can't always multiply matrices, and it's not just that they have to be the same size. In fact, sometimes if you've got matrices which are identical in dimensions, they can't be multiplied. What you need to make them multiplicable is that you need the number of columns in the first matrix to be equal to the number of rows in the second. So, and then we get another thing there. The number of rows of the first and the number of columns in the second give you the dimensions of the result. So, square matrices, you know, a 2 by 2 can always be multiplied by a 2 by 2 or a 3 by 3 by 3 by 3. It's not always the case with a non-square matrices. Another thing that comes across is that when we multiply matrices, the order does matter. If you multiply in the wrong order, you get different results. They're not commutative like ordinary addition, as possibly the first time you've seen this, where multiplication doesn't work. A times B is not equal to B times A. Well, generally it's not. Sometimes it is. But generally in matrices, you won't get the same answer. So what we're going to do is we're going to see if we can see what sort of matrices we can multiply. We can multiply a 3 by 3 by another 3 by 3. Easy peasy. That, well, not easy peasy, but it's simple to see. See, the number of columns in the first matrix, which is 3, is the same as the number of rows in the second matrix. And our answer is the outside 2 there. A 3 by 2 works, multiplies by a 2 by 3. Fine, because look, the 2 by 2, the two columns in the first and 2 rows in the second, giving you a result of a matrix which is 3 by 3. But we can't multiply a 2 by 3 by another 2 by 3 because look, the 3 rows in the first, 3 columns in the first matrix are only 2 rows. It won't work. It's another example of an impossible multiplication. There's a big one. We'd get a 4 by 3 multiplied by a 3 by 4 gives us a huge matrix, 4 by 7, 28 elements. So the practice is it's really not obvious at all, okay? But there's a little phrase I have which I find helps me, which is to think row by column every time. So we look at dealing with a row and a column together. Okay, so let's start with a fairly small one, a 2 by 2, two by 2 matrices. And it's certainly conformable because the number of columns in the first is equal to the number of rows in the second. Okay, so this is what we do. We're going to look at the first row, 1, 2, and multiply it by the first column, 5, 7. Now by multiply, I mean 1 multiplied by 5 plus 2 multiplied by 7. I'm going to show you, write this down for you in a moment, but then we do the same with the first row and the second column, 1 by 6 plus 2 by 8. Then we go to the second row, 3 by 5 plus 4 by 7. And we go to the second row and second column, 3 by 6 and 4 by 8. You see that? So it's worth, when you're doing this at first, to write down that a few times. Okay, don't try to do it in your head yet. So 1 by 5 plus 2 by 7, 1 by 6 plus 2 by 8, 3 by 5 plus 4 by 7, 3 by 6 plus 4 by 8. And then the answer is just pure arithmetic. Okay, so that's it. Okay. Now it's going to be quite common for us to multiply a square matrix by a vector. So a vector which has got 2 rows and 1 column. That's going to be important for multiplying for working out simultaneous equations. So 5 times minus 2 plus 6 times minus 8. The first row times the first column. Well, there's only 1 column, so we can only do that. Then 7 times minus 2 plus 8 times minus 8. The second row times the first column. That's it. And that gives us minus 58 minus 78. Okay, so something a little bit bigger. A 3 by 3 by 3 by 1. The first row times the first column. 1 times 1, 0 times 2, 1 times 3. Then the second row times that first column. 1 times 1 plus 1 times 2 plus 1 times 3. And likewise with the third row. 2 times 1 plus 1 times 2 plus 0 times 3. And then we get that vector there, 4, 6, 4. We could do this 2 by 3 by a 3 by 2. We're not gonna do many like that. I think you'll do this a little to practice in some of the early exercises, but so that it works. 2 by 3 by 3 by 2. The number of columns in the first is the same as the number of rows in the second. So it's going to be 1 by 1 plus 1 by 0 plus 1 by 1. First row times the first column, first row times the second column. So 1 times 3, 0 times 2, 1 times 0. And the same with the second row. Second row times the first column, second row times the second column. And we get from that, those two large matrices, you get a smaller one. It's quite strange, isn't it? But it is. It's as the dimensions predict, 2 by 2 is what you get. Okay, so I suggest that you work through these. I've tried to minimize the amount of grind, but sometimes it's a little bit necessary. So just 2 exercises to work on. Exercise 1A and those questions, which I think, if memory serves, is basically dimensions and add-in and some relatively straightforward stuff. And then B is about matrix multiplication, and I'm afraid you've got to do the practice. You really have to go through quite a few of these to get the feel for this project. Okay, so let's just move on. Really very important idea here, and I'm going to perhaps labor this point because I wanted to make the idea of an inverse really clear. It's very important in abstract algebra, a very, very important concept, but you know it really. And I'm just going to look at this trivial equation 4x equals 12, and of course the answer is 3. You can see that straight away. But and what you've been doing in the past is you just divided both sides by 4. But I just want you to think about it slightly differently, and instead of multiplying both sides by dividing both sides by 4, multiply both sides by a quarter. It's clearly exactly the same thing. I'm spelling it out there in ridiculous detail. Okay, obviously multiplying by a quarter is the same as dividing by 4. And then we get, of course, get the same answer. Okay, 1x equals 3, because 1 times 4 is 1, and we don't bother writing down the 1. So solution is 3. And then, as I said, I'm laboring this. We can check it by saying 4 times 3 is indeed equal to 12. Okay, so let's just take this on a little bit for a more general version of the same equation, ax equals b. So we multiply both sides by 1 over a. The a's cancel on the left-hand side. It gives us 1. That's equal to, gives us the solution, x is b over a. Okay, now, clearly I'm not expecting you to do this for linear equations, but I'm trying to show you that there is some reason behind what we do, and the notation will make a lot of sense. So we could use this different notation. You do know that 1 over a can be written as a to the power minus 1. Okay, so same thing. We pre-multiply by a minus 1 for both sides. A minus 1 times a is 1. And that gives us our solution. X is a to the minus 1b. Okay, and this is important. This is an important idea. A to the power minus 1 is the multiplicative inverse of 1, since when we multiply those two things together, the result is 1. Doesn't matter the order. So later we're going to be solving some matrix equations, and we'll do this in more detail later, but they can be written in this form. Capital AX equals B. So A is a matrix, okay? X is a vector, it's a column vector, as is B. Okay, now we'll see this work shortly, but let's see how this works in an abstract sense first. So we do exactly the same thing. We pre-multiply, we multiply by A to the power minus 1 on both sides. Now I've written there I instead of 1. Now I is the matrix equivalent of 1. It's called the identity. Now an identity is a very boring thing. If you multiply something by an identity, it makes no difference to it whatsoever. It's the equivalent of 1. So 1 times 5 is 5. 5 times 1 is 5. Now that means we can just drop the I. So our result, and you'll see this shortly. The result is going to be A minus 1 times B, and you have to do a little bit of multiplication there. So this identity matrix is, as I said, the equivalent of 1. When we multiply a matrix by it, nothing happens. So 1 times 2 is 2 times 1 is 2. IA equals AI equals A. Now then I've given you an example of the smallest identity matrix. They're always square, and they always look like this. They're always made up of ones and zeros. There's nothing else there. And to show you, give you the pattern better, I3 for a 3 by 3 has ones along what we call the leading diagonal and zeros everywhere else. And that's true for any size matrix. 4 by 4 would look the same. It's just got 4 rows, 4 columns, and ones going down the leading diagonal. Okay, so we're on a march to find an inverse matrix, which for 2 by 2s isn't too bad, but for 3 by 3s is a bit of a pain. Unfortunately, you're going to have to learn to do it. So what's a determinant? Now a determinant has a geometrical function, which we'll see from matrix when we do matrices with transformations, but it's a number, okay, and it's unique to each matrix. Only square matrices. We're only going to deal with square matrices. So this is the first step in finding an inverse matrix. So the determinant for 2 by 2s and 3 by 3s is okay. It's a lot more. If you go bigger than a 3 by 3, it's quite a lot of work. Very straightforward for 2 by 2. It's just what we'd say is it's the difference between the products on the leading, so it's the product of the elements on the leading diagonal subtract the product of the elements on the trailing diagonal. So given this example, the leading diagonal has 1 and 4, the trailing diagonal has 3 and 2. So the determinant, which is written as det A, which I will tend to do, or can be written as A, as like mod A, is going to be 1 times 4 subtract 3 times 2, and it's minus 2. That's it. That's all there is to it. So for B, it's going to be minus 2 times 8 subtract 3 times minus 7. Be careful with your signs, but that gives us 5. And in general, well, it's easy to write it down in general. It's A times D minus B times C. That's it. So for 2 by 2, this finding a determinant is pretty straightforward. And it relates to when you do transformations, the determinant will give you the scale factor, the change in the area of the object. Now then, this one's a little bit interesting. 3, 6, 2, 4. So if we looked at the determinant of that, it's going to be 0. 12 minus 12 is 0. Okay, and that's called a singular matrix, and it gives us a few problems. Okay, basically you can't find the inverse of a matrix with a singular matrix. Okay, so it's always something like this. The inverse of a matrix, no matter what the size is, it's 1 over the determinant times what we call the adjunct. Okay, and the adjunct depends on the size of the matrix. For a 2 by 2, it's quite straightforward. It's not for a 3 by 3. It really is a pain for a 3 by 3. So in this stage, we're only going to consider 2 by 2. As I said, unfortunately, we're going to have to deal with finding 3 by 3s. So here we go. For that matrix, the adjunct matrix is just you swap the elements on the leading row, on the leading diagonal, and change the signs on the trailing diagonal. That's it. See, A and D are swapped, and I put minus signs in front of the other two elements. I've changed their signs. That's it. There's nothing more to it. So there we go. For B, I'm going to swap the 8 and the minus 2, and I'm going to change the signs on the 3 and the minus 7. You see? 8, minus 2, minus 3, and 7. See how they swapped? So B minus 1, the inverse of B is well, so let's first of all quickly work out its a determinant. So the determinant will be minus 16, minus 2 times 8, take away 3 times minus 7, which is effectively plus 21. So that would give us a 5. So the determinant of B is 5. So therefore the inverse of B is 1/5 of 8, 7, minus 3, minus 2. Now if we multiply that by our original matrix, we would, I promise you, we would get 1, 0, 0, 1. We'd get the identity matrix. Try it if you don't believe me. So here's another example. The determinant is 25. 21 minus 4 is 25. So the inverse is 1/25. Swap the 3 and the 7. Change the signs on the minus 4 and the 1. That's it. And to check, to prove to you. Okay, so if we multiply them together, we're doing E minus 1 times E here. So we're going to first of all multiply the matrices, which would give us, going through this same process, 7 times 3, minus 1 times minus 4, etc., row by column, row by column. That gives us 1/25 of 25, 0, 0, 25, which is the identity matrix 1, 0, 0, 1. And it works the other way. We've just shown that E to the minus 1, E gives us I, the identity, but also E times E minus 1 will also give us the identity. If we swap the order around, it would work fine. We can put that scalar, the 1/25 at the front, whichever order we do the matrices in. So here's another example. Determinant, well, determinant, I'm doing the whole thing in one go here, showing the calculation for the determinant and getting the adjunct. Okay, and then I'm checking it. And it works. Okay, and you can go through those carefully if you wish, but that's it. It's probably worth checking it for yourself. So there you go. Singular matrices, a matrix with a 0 determinant will not have an inverse. Okay, so again, have a look at those. These are to do with inverses, determinants and inverses. And again, you've got to be work patiently through these. Okay, so I'd like to show you why you do this, and this is going to be done more thoroughly in, I think, is chapter 3, a little bit further on. So one reason for doing this is we can solve simultaneous equations using matrices. And you can say, well, why do we need to bother really? Because it's easy enough. But the point is that we use the same technique effectively to solve 2 equations in 2 unknowns as we used to use 5 equations in 5 unknowns. Now, in practice, you'd want to train a computer to do this because it's a lot of calculation, but that's a handy principle. So if we look at this pair of equations, I hope it's relatively clear that the solution to this is when x is 1 and y is 1. Okay. But this is just meant to be an illustration of how this works. And what I'm going to do is rewrite this in matrix form. Okay, matrix form looks like that. And this makes sense because if we looked at multiplying the left-hand side, we'd have 2x plus 3y in the first row equal to 5. And in the second row, 5x minus 7y equals minus 2. It's the same. It's the same as those equations there. So what we have is A times X equals B. A is the matrix, X is the vector of the unknowns, and B is our solution, our known values. So I went through the work and I worked out that A minus 1 was minus 1 over 29. They're often ugly fractions like this. Minus 7, minus 3, minus 5, 2. Okay, so what we're going to do is from this, we're going to multiply both sides by A minus 1. Now on the left, if I multiply my inverse matrix by 2, 3, 5, minus 7, I'll get the identity, or 1, the matrix equivalent of 1. On the right-hand side, I've got to do a little bit of multiplication. The numbers are a little bit awkward, but it does give me x is 1 and y is 1 in just the same way. Okay, so that's why we do it, and the principle is the same for 3 by 3s and 4 by 4s. We can do that. Okay, so I wish they wouldn't teach this. Actually, it's a pointless thing to do. Your calculators will do this. But nonetheless, you've got to be able to do this. For the questions in the exam, they do force you to be able to do this. So a determinant of a 3 by 3 first of all. Okay. I mentioned there's another method called Cramer's rule, but it's perhaps a little bit less work than the way I'm going to show you, but still involves finding determinants of matrices. Okay, so finding the determinant. Those of you who might go on to do economics, I've seen them use Cramer's rule in economics. So what we're going to do is we're going to find the inverse of this function, and we're going to start by finding the determinant. Now, this little grid, plus, minus, plus, minus, plus, minus, and so on, that's going to be important to us. So just bear this in mind, okay, this kind of checkerboard pattern. That statement is really quite difficult to understand. Each element in the grid has a matrix of cofactors consisting of all the elements outside that element's row and column. And you'll see this as I solve the problem. So if we look at the 1 in the top left-hand column of A, what's not in that elements row? Well, that elements row is the 1, 2, and 3, and that elements column is 1, 4, and 7. So we want everything that's not in that. Minus 5, 6, 8, and 9. If I looked at 8, we have to wipe, but we have to ignore the bottom row and ignore the middle column. So what we'd have is 1, 3, 4, 6. Okay. Now what we're going to have to do is I'm going to do this more than is necessary. I'm going to do 3 versions of the same thing, 3 ways to get to the same answer, okay, for this particular one. But let's have a look. The determinant. So there you go. If we looked at row 1, the determinant, we could find the determinant by multiplying each element by its matrix of cofactors and adding them up according to the checkerboard pattern. So we've got +1 times its cofactors, the elements outside its rows and columns. Then why have I written -2? Because the checkerboard pattern, it goes plus, minus, plus, minus. So it's 2 times the cofactors for 2. Cofactors for 2 are 4, 6, -7, and 9. They don't appear in the row or the column of 2. And 3 plus, minus, plus, 3 times the determinant of 4, -5, -7, 8. And there I've done the calculation, it gives us -258. Now we could do the same for row 2. So row 2 would be, now remember the checkerboard pattern. The checkerboard pattern plus, minus, plus, minus in the second row, plus, minus. So we've got -4 times its matrix of cofactors, 2, 3, 8, 9, which outside its row and column. Similarly, we're going to have to add -5 times its cofactors and then subtract 6 times its cofactors. And it gives us the same result. The determinant is the same. For row 3, the same. So row 3, the signs go plus, minus, plus, plus, well, it's -7 times its cofactors, 2, 3, -5, 6, and so on. It gives us the same answer. Now, I've just shown you that we get the same answer whichever row we take here for the determinant. Habitually, I will only work with row 1, unless if you spot a lot of zeros in one of the row, that can make your calculation a bit less effort. You do only have to do it once. Okay, this is going to get worse now. So if the matrix is non-singular, it's worth going on to try to find the inverse. So you're going to find the adjunct. Confusing. It's the adjunct of the matrix of cofactors using the same grade of plus or minus signs as before. So you're not going to like this. So there's our matrix. Okay, our matrix of cofactors looks, you ready for this? Looks like that. So can you see the first pattern? Plus, minus, plus, minus, plus, minus, and so on. So there we got the pattern. Can you see the T for transpose? Don't forget to transpose it. It's easily done. So the first, the cofactors of the 1, as we did before, were -5, 6, 8, and 9. The cofactors of the 2, we don't write down the 2, there's no the 2, forget about the 2 now. The cofactors were 4, 6, -7, and 9. And so on. And this, as you imagine, is quite not just tedious, but it's exacting and easy to make a mistake. So you've got to work out the cofactors carefully, and then you've got to work out each of those determinants, and that's not easy. So the determinant of the first one, we've got -5 times 9 8 times 6 will give us that -93 in the first row in the first column. And we've still got to transpose it. So we've got to swap the rows and columns. Again, easy to make a mistake. The first row, -93, -78, -3, becomes the first column. Second row, 630 to -22, second column. Are we there yet? Well, more or less. So the inverse of this matrix is 1 over 258 times that matrix there. And I did go ahead and check it, and it works. It gives us the identity matrix. So finally, in that textbook, you need to have a look at exercise 1E, which is practice on 3x3 matrices, and exercise the next practice at the end. So what I'm going to advise you to do is you really must do these by hand. If you've already worked out how to use it do it with your calculator, brilliant. But do these by hand. If you haven't worked out how to do these with a calculator, you can do it with the Casio CG50, the TI Inspire, or even the more basic version, the Class Wiz. It's a bit of a faff, to be honest, on the Class Wiz. It's on these big graphical calculators, it's a little bit easier. Okay, so that's everything.